Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be back. We got a really great deep dive for you today.
Yeah, we do. So I want you to imagine staring through the Lexan window of a multi-axis CNC mill. And inside is a $50,000 block of aerospace-grade titanium.
Oh man, just thinking about that makes me sweat a little.
Right, because the spindle is buried deep in a roughing pass, and suddenly the machine starts screaming.
Like literally screaming, the whole floor vibrates.
Exactly. The tool chatters, and every single human instinct in your body is begging you to hit the emergency stop. Or, at least drastically slow down the feed rate.
Which is, ironically, the absolute worst thing you could do in that moment.
Yeah. Because if you ease off the gas right there, you will instantly work hard in the metal, you'll shatter a $500 carbide insert, and potentially scrap the whole component.
And you can't recover from that. It's a very visceral experience, really.
Yeah, it is. So today, we are doing a sort of masterclass. We're going to explore the brutal, counterintuitive physics of why that happens and map the whole journey for you.
Yeah, it perfectly illustrates the central tension of engineering. We're going to trace the entire life cycle of a mechanical component today.
From the very beginning.
Right. We'll start in the pristine, idealized world of mathematical modeling where everything is, frictionless and perfectly linear.
But we definitely won't stay there.
No, we won't. We're going to track that theoretical model as it gets dragged, kicking and screaming, into the messy reality of fluid dynamics.
And the punishing thermal taxes of thermodynamics.
Exactly. And finally, onto the unforgiving factory floor, where we actually have to cut the metal and hit a tolerance.
I love that framing because as engineers, we often get siloed.
Constantly.
Like the controls guy is staring at a Laplace transform, the thermal engineer is battling a CFD simulation, and the machinist is just trying to stop the titanium from catching fire.
But the secret is, it's all the exact same physics, every bit of it.
It really is. So let's start at the beginning of a design's life, the theoretical model.
Right. Before we ever cut metal, we have to simulate how a dynamic physical system will behave.
Because it's too expensive not to.
Exactly. Modern control systems rely entirely on mathematical models using difference or differential equations.
A model is just infinitely easier, safer, and cheaper to study than the physical system itself. You can test failure modes in a computer without actually breaking anything.
But here's the problem. The physical universe is, well, it's impossibly complex.
Yeah, like if I'm designing a suspension for a Baja racing truck, I can't write an equation for every single grain of sand hitting the shock absorber.
Right, or the exact molecular friction of the hydraulic oil.
The math would be totally unsolvable.
It would. So we abstract it. We build what the literature calls lumped element models.
Lumped elements, I always like that term.
It's descriptive.
Mm-hmm.
That abstraction relies on categorizing components based purely on how they handle energy, while completely ignoring their physical shape.
Okay, so what are the categories?
We use three main ideal elements. First, you have T-type elements, which are inductive storage elements.
Like a mass.
Exactly. In a mechanical translation system, this is a pure mass storing kinetic energy based on its velocity.
And in an electrical circuit.
It's an inductor storing energy in a magnetic field based on current.
Got it. Then we have A-type elements, which is the capacitive storage, right?
Right. Mechanical spring storing potential energy based on its displacement, or a capacitor storing energy in an electric field based on voltage.
Okay, so that's T-type and A-type. And the last one?
The D-type elements. These are the resistive elements.
So they don't store energy.
No, they dissipate it. They usually just bleed it out of the system entirely as heat. A mechanical dashpot or a viscous damper fits here, just like an electrical resistor.
Okay, here is where the elegance of this really hits me. We take a highly complex physical assembly, say, a rack and pinion steering gear.
Right.
And we are just pretending it is a network of pure masses, pure springs, and pure dampers.
Yeah, we strip away all the geometry.
And the reason we can do this across entirely different domains, like mechanical, electrical, fluid, thermal, is because of the universal nature of power flow.
Power flow is the great equalizer in physics. I mean, mathematically, power flowing into any of these elements is defined in the exact same way.
It's the product of the through variable and the difference in the across variables, right?
Yes.
Yeah.
Let's break those terms down for you because that nomenclature is crucial to understand.
Yeah, let's do that. So what is a through variable?
Think of a through variable as the quantity that physically passes through the element.
Okay, so in a mechanical system, force is transmitted through a spring.
Exactly.
Hmm.
And in an electrical system, current flows through a resistor.
That makes sense. And the across variable.
The across variable is the measurement taken across the two ends of the element. So in a mechanical system, one end of a damper might be moving at 5 meters per second, and the other end at 2 meters per second.
So that difference in velocity is the across variable.
Right. In electrical terms, it's the voltage difference across a component.
So the generalized power equation for any of these lumped elements is really simple. It's just P equals the difference between V2 and V1, all multiplied by F.
Exactly. P equals the difference between V2 and V1, all multiplied by F.
It's so clean.
It is. If F is electrical current and the V's are voltages, that's electrical power. If F is fluid volumetric flow rate and the V's are pressures, it's fluid power.
The mathematical structure remains identical.
Identical. And it's not just these single-port elements that share this math. The sources also dive into multi-port elements.
Right, things that transform or route energy without inherently storing it, like transformers and gyrators.
Yeah, transformers are highly intuitive. A mechanical gear train is a perfect transformer.
Because it takes a high-speed, low-torque input and transforms it into a low-speed, high-torque output.
Exactly. The through and across variables change ratios, but if we assume ideal conditions, the total power remains constant.
And an electrical transformer does the exact same thing with voltage and current.
Yep. Now, gyrators are a bit more of a brain bender.
Oh yeah, they definitely are.
A gyrator cross-links the variables. It takes the across variable at port 1 and links it to the through variable at port 2.
So what's a real-world example of that?
A classic mechanical example is a gyroscope. If you apply torque, which is a through variable around one axis, the gyroscope responds with a precession velocity.
Which is an across variable.
Right, and it responds around an entirely different perpendicular axis.
I see this constantly in systems engineering. Teams waste weeks fighting over simulation discrepancies because they've totally overcomplicated their lumped element models.
Oh, I see it all the time too.
Yeah.
There's this pervasive belief that throwing more computing power at a model inherently makes it a better model.
Like, if I capture every microscopic physical detail, it's somehow more accurate.
Right, but it's actually a fundamental misunderstanding of what engineering is.
Let's go back to that Baja truck suspension.
Okay, good example. In physical reality, that heavy steel spring has its own mass. As it compresses, it has internal material friction.
And if the trick bottoms out, the coils bind together and the spring rate becomes violently nonlinear.
Exactly. So if you try to model every single one of those secondary characteristics, you generate a massive matrix of stiff differential equations.
Which takes hours to compute.
Hours. And it becomes highly sensitive to initial conditions. It's a mess.
But wait, let me push back a bit. If I completely ignore the mass of a 20-pound steel spring, aren't my eigenvalues going to be off?
Technically, yes.
So I'm technically designing a system that doesn't exist in reality.
Well, you are building an abstraction.
Yeah.
And the validity of that abstraction depends entirely on the operating frequency of your system.
Okay, explain that.
If the unsprung mass of the wheel assembly is 200 pounds and the chassis mass is 2,000 pounds,
Yeah.
the dynamic effect of the spring's 20-pound mass at the low frequencies a truck suspension normally operates in is effectively invisible.
Oh, I get it. It just falls into the noise of the calculation.
Completely. It doesn't matter.
It's like drawing a map of a city. If I try to draw a map at a 1-to-1 scale, detailing the exact location of every single fire hydrant, pebble, and blade of grass.
You'd have a very big map.
Right. The map is technically perfectly accurate, but it's also completely useless because I can't unfold it in my car.
Yeah, that's a great way to put it.
To make the map useful for navigation, you have to aggressively throw away information. I delete the grass, I delete the hydrants, and I just draw a red line for the highway.
That is the perfect analogy. The art of dynamic modeling is ruthlessly discarding physical reality until you are left with the simplest mathematical structure that still accurately predicts the specific behavior you want to control.
Okay, so we've built our elegant, frictionless mathematical abstraction. We know how the masses and springs should theoretically behave.
Yes.
But the second that suspension actually cycles, the damper forces fluid through an orifice.
Which generates friction.
Which generates heat. So we are instantly kicked out of the pristine mathematical domain and thrown right to the wolves of fluid dynamics and heat transfer.
And that transition requires a severe shift in our analytical approach. In dynamic modeling, we use idealized lumps. But in fluid mechanics, we have to deal with the continuum.
The chaotic, distributed reality of a fluid in motion.
Right, and one of the primary tools we use to bridge the gap between small-scale testing and large-scale reality is dimensionless analysis.
Specifically, utilizing the Buckingham pi theorem.
Yes.
Dimensionless numbers are fascinating because, they honestly feel like cheating. We are literally stripping the units away from our physics so we can scale things up and down.
Well, it isn't cheating. It's actually a deep recognition of how fundamental physical forces balance each other.
So how does the Buckingham pi theorem actually work in practice?
It allows us to take a massive list of variables governing a fluid system like fluid density, viscosity, velocity, pipe diameter, surface roughness, and group them into a smaller number of dimensionless parameters.
Like the Reynolds number or the Mach number.
Exactly. Take the Reynolds number, for example. It is not just a random calculation.
Right.
It represents the physical ratio of inertial forces, the momentum of the fluid pushing forward, to the viscous forces, which is the internal friction of the fluid trying to drag it to a halt.
And if that ratio is identical, the fluid behaves identically, regardless of the physical size of the system.
That is the principle of dynamic similarity.
Which is why an aerospace company can put a 1/20th scale model of a Boeing 777 wing into a wind tunnel.
Yep. Pump highly pressurized cryogenic nitrogen over it to match the flight Reynolds and Mach numbers.
And extract aerodynamic data that flawlessly predicts how the full-size wing will behave at 35,000 feet. It's wild.
It is wild. But even armed with dimensionless analysis, fluid mechanics fights you every step of the way.
Oh, definitely. When I think about the sheer amount of time engineers spend just trying to size a basic pipe network,
Yeah.
it's brutal.
It really is.
You are looking at a pump curve, trying to calculate the required pipe diameter for a specific pressure drop, but the math is completely cyclical.
You are referring to the implicit nature of pipe friction calculations, specifically when you're using equations like the Colebrook-White equation.
Yes, it is a classic trap. To calculate the pressure drop across a pipe, you need to know the friction factor.
But to find the friction factor, you have to calculate the Reynolds number, which dictates whether the flow is laminar or turbulent.
Right. But to calculate the Reynolds number, you need to know the fluid velocity.
And to know the velocity, you need to know the pipe diameter, which is the very thing you are trying to solve for in the first place.
The variable you need is literally buried on both sides of the equal sign. I remember writing Python scripts specifically to run numerical solvers on this because doing it manually makes you want to tear your hair out.
Oh, I've been there.
If you guess a velocity of 0 to start your solver, the whole script just crashes.
Which is exactly why you must embrace the iterative method. But you have to do so strategically. You have to seed the calculation with an educated guess.
Okay, so how do we make a good guess?
If you look at a Moody chart, which maps the friction factor against the Reynolds number and relative pipe roughness, you'll notice something critical on the far right side of the graph.
What's over there?
At very high Reynolds numbers, the flow is fully turbulent, and those friction factor curves flatten out into horizontal lines.
Ah, I see. Meaning that once the flow is chaotic enough, the internal fluid viscosity matters less, and the physical roughness of the pipe wall dominates the friction.
Precisely. Because it goes horizontal, the friction factor becomes essentially independent of the exact Reynolds number in that region.
Oh, wow. So your educated first guess is always to just assume fully turbulent flow for your specific pipe material?
Yes. You pull that friction factor, plug it into the Darcy equation, and calculate a preliminary velocity.
And now that I have a preliminary velocity, I can actually calculate a real Reynolds number.
Yes. You use that preliminary velocity to calculate a new Reynolds number, go back to the Moody equation, and find a much more accurate friction factor.
And then you just run the Darcy equation again.
Exactly. You repeat this loop until the velocity you calculate perfectly matches the velocity from the previous iteration. The math literally converges on reality.
It reminds me of tuning a fluting bridge guitar like a Stratocaster.
Oh, how so?
Well, you tune the low E string up to pitch, but adding that tension pulls the bridge forward, which slacks all the other strings.
Oh, wait.
So you tune the A string, which pulls the bridge a little more. Detuning the E string, you literally just fixed. You can't just tune each string once.
Right, you have to iterate.
Yeah, you have to make a pass, get close, then go back to the first string, make a smaller adjustment, and iterate across the fretboard until the entire mechanical system reaches equilibrium.
That is exactly what an iterative numerical solver is doing, seeking equilibrium. And we see this exact same interdependent behavior in heat transfer, too.
Because the systems are intimately linked. After all, the fluid flowing through that pipe is usually carrying thermal energy.
Exactly. The sources categorize thermal systems into three fundamental modes: conduction through solid matter, convection through moving fluids, and radiation through electromagnetic waves.
Though we'll mostly focus on conduction and convection here, along with phase change, which is really just a chaotic subset of convection.
Right. So let's drill down into a very specific, really common problem: radial heat conduction through a hollow cylinder.
Okay, lay it out for me.
Imagine a high-pressure steam line running through a chemical plant. You need to calculate the exact amount of thermal insulation to wrap around it so you don't lose your process heat to the ambient winter air.
The math here is tricky, though, because unlike heat moving through a flat wall where the surface area is constant, the surface area of a pipe increases the further out you go from the center.
That geometric reality changes the calculus entirely. Because the area expands radially, the thermal resistance isn't linear.
Right, the outer layers of insulation have way more surface area than the inner layers.
Exactly. If you integrate Fourier's law of heat conduction in cylindrical coordinates, you actually end up with a natural logarithm.
Okay, let's walk through that math structure.
The model for the heat flow Q looks like this. Heat flow Q equals the difference between T1 and T2,
Okay.
divided by the natural log of R2 over R1,
Right.
which is then divided by 2 pi KL.
Okay, let's map those variables for everyone listening. T1 is the hot steam temperature inside the pipe, and T2 is the cold exterior temperature.
Correct.
The radii, R1 and R2, are the inner and outer dimensions of the pipe wall. The K is the thermal conductivity of the steel, and L is the length of the pipe run.
That's right. And that natural logarithm, the ln of R2 over R, dictates something really important.
What's that?
It means that adding an inch of insulation to a small 2-inch pipe has a drastically different thermal effect than adding that same inch of insulation to a massive 40-inch pipe.
Oh, because the ratio is completely different?
Exactly. But the real engineering problem happens when you realize you don't actually know T1 and T2 at the pipe surfaces.
Right. I only know the temperature of the steam flowing inside and the air blowing outside. I don't know the exact temperature of the steel itself.
Which means you have to add convective thermal resistance to the inside and outside of the conduction equation.
And convective heat transfer coefficients are highly dependent on the fluid velocity.
Which brings us right back to our iterative fluid mechanics problem.
Oh man, it's a trap. The fluid friction dictates the velocity. The velocity dictates the convective heat transfer.
Yep.
And the heat transfer changes the fluid temperature, which changes the fluid viscosity, which alters the fluid friction.
It is an endless, inescapable loop.
And this constant balancing act, this realization that every time we move fluid or transfer heat, we lose something in the process, it naturally leads us to the grim reality of thermodynamics.
It is the universal tax.
The universal tax. I like that.
Classical thermodynamics rests heavily on two pillars for mechanical engineers. The first law, which is essentially the conservation of energy.
Dictating the equivalence of work and heat.
Right. If energy goes into a system, it must come out or be stored.
And then the second law introduces the concept of irreversibility, the unavoidable generation of entropy.
Entropy. The universe's relentless march toward disorder.
But how does that philosophical concept actually dictate the shape of the physical hardware we design?
Let's look at a basic open system component, like an expansion turbine in a jet engine.
Okay.
Hot, high-pressure exhaust gas rushes into the turbine blades, turning them to produce mechanical shaft work.
Right, spinning the turbine.
Under the first law, assuming it's perfectly insulated, the work output simply equals the mass flow rate multiplied by the difference between the specific enthalpy entering the turbine and the specific enthalpy exiting the turbine.
Energy state in minus energy state out equals the rotational work done on the shaft. It makes perfect sense.
It does. And the first law works identically in reverse for a compressor,
where you input mechanical shaft work to take low-pressure air and crush it into a high enthalpy, high-pressure state.
Exactly. Or take a nozzle, which doesn't use shaft work at all. It merely trades the fluid's enthalpy for raw kinetic energy, accelerating the flow.
But the first law doesn't tell the whole story, does it? I mean, it tracks the quantity of energy, but it completely ignores the quality.
That is the crucial distinction. Classical thermodynamics often utilizes idealized, reversible processes as its baseline.
And a reversible process is a total fantasy.
Pretty much. It's a fantasy where a system can move from state A to state B and then be pushed perfectly back to state A without leaving a single trace of change on the rest of the universe.
But we know that's physically impossible. I mean, if I compress a gas, it heats up. If I expand it, it cools down. There's friction against the cylinder walls. Heat leaks out.
Exactly. Reversible processes require things to happen infinitely slowly, meaning infinite
Mm.
time, so that there are no temperature gradients and no fluid friction,
They also require infinite size, like a heat exchanger with an infinite surface area.
which is the exact opposite of what an engineer actually deals with. We are always constrained.
Yeah, we have milliseconds to combust fuel in a piston, and we have to fit the radiator inside the incredibly tight aerodynamic cowling of a Formula One car.
This profound disconnect between classical, infinite-time thermodynamics and real-world engineering led to the development of EGM.
EGM, entropy generation minimization.
Right. This is a framework that specifically analyzes systems constrained by finite size and finite time.
So instead of pretending the process is reversible, EGM accepts the irreversibility and tries to mathematically minimize it.
Yes. EGM combines thermodynamics, fluid mechanics, and heat transfer into one holistic optimization problem.
So how does it define that loss?
It recognizes that any irreversibility like thermal resistance or fluid friction destroys what we call exergy.
Exergy, let's define that for the audience.
Exergy is the maximum theoretical useful work you could possibly extract from a system as it comes into equilibrium with its surrounding environment.
So when entropy is generated, exergy is permanently destroyed.
Yes, we call this lost available work.
Let me ground this in a real-world scenario to see how this optimization actually plays out.
Go for it.
Let's say I'm designing that heat exchanger for the Formula One car. My goal is to reject heat from the engine oil to the outside air.
Okay.
To improve the heat transfer, my instinct is to add hundreds of tiny aluminum cooling fins inside the tubes to massively increase the surface area.
But look at what happens when you do that. Yes, adding those fins decreases the thermal resistance, which lowers the entropy generated by the heat transfer process across a temperature difference.
Right.
But by packing the pipe with hundreds of tiny fins, you have drastically increased the fluid friction.
Oh, because the oil has to squeeze past all those fins.
Exactly. The oil pump now has to work twice as hard to force the viscous oil through those narrow channels,
And that fluid friction creates a massive pressure drop.
which generates a huge amount of its own entropy, permanently destroying the pump's mechanical exergy.
So the thermal physics and the fluid physics are actively fighting each other? If I optimize purely for heat transfer, I choke the flow and destroy pump efficiency. If I optimize purely for fluid flow by using a wide, smooth pipe, the heat transfer plummets, the engine oil overheats, and thermal entropy spikes.
That is the absolute genius of EGM.
So how do you find the balance?
You write a mathematical objective function for the total entropy generation rate of the entire system, incorporating both the thermal gradient terms and the fluid friction terms.
And then,
Then, using calculus, you find the precise physical geometry, the exact fin length, the exact tube spacing, where the sum of the thermal entropy and the friction entropy hits its absolute mathematical minimum.
you are actively balancing the taxes.
Yes, you are paying the universe exactly what it demands and not a penny more.
That is incredible. We are literally using the physics of decay to optimize the geometry of the design.
It's beautiful in a way.
It is. Okay, so we've iterated our fluid loops, we've balanced our entropy taxes, and we have a fully optimized, mathematically sound CAD model.
But now, the theoretical journey ends.
Yeah. We have to take a solid block of raw material and violently rip it apart to create the shape we designed. We have to cut metal.
And this transition to machining is often where theoretical engineers get a really harsh reality check.
Oh, absolutely.
When a carbide cutting tool shears material off a workpiece, the pressures and temperatures at that microscopic cutting edge are extreme.
And the metallurgy of the workpiece completely dictates the rules of engagement.
Completely. If you look at standard machining handbooks, the surface speeds and feed rates vary wildly depending on what you are cutting.
Like plain carbon steel cuts entirely differently than an austenitic stainless steel or an aerospace superalloy like Inconel.
Exactly. Plain low-carbon steel is relatively forgiving. The chips shear cleanly, and the heat mostly flows out into the chip itself, carrying thermal energy away from the tool.
But austenitic stainless steels, like the common 304 or 316 grades, have a totally different crystalline lattice structure.
They do. When the cutting tool violently deforms that lattice at the shear plane, dislocations pile up.
The material actively resists deformation, and the surface immediately becomes harder.
This is work hardening.
So the very act of cutting it actually makes it harder to cut.
Exactly. And then you have titanium alloys.
Titanium is exceptionally strong and lightweight, but it is notoriously difficult to machine.
Right, because it has incredibly poor thermal conductivity.
Wait, why is that? Why doesn't it conduct heat like steel or aluminum?
It comes down to its atomic structure.
Hmm.
Thermal energy in metals is primarily transported by free electrons.
Okay.
Titanium has a much lower density of these highly mobile free electrons compared to something like copper or aluminum.
So when you machine titanium, the massive amount of frictional heat generated at the shear zone cannot dissipate quickly through the workpiece.
Exactly.
So where does the heat go?
It goes directly into the cutting tool. The temperature at the tip of the carbide insert skyrockets.
And that extreme heat leads directly to tool failure.
It does. The literature categorizes several specific types of wear we have to watch out for. Flank wear, cratering, frittering.
Let's define those. Flank wear is the most standard, right?
Yeah, it's the physical abrasion on the side of the tool that rubs against the newly machined surface of the part. You can literally measure the wear land with a microscope to know when the tool is dead.
And cratering, that is deeply tied to the heat we just discussed, isn't it?
It is. Cratering happens on the top face of the tool.
Where the hot chip curls up and drags across the insert.
Yes. But it's not just physical friction gouging out a crater. At those extreme temperatures, a chemical diffusion process actually occurs between the hot steel chip and the tungsten carbide tool.
Wait, a chemical reaction?
Yeah. The tool material literally dissolves into the chip and is carried away, leaving a crater behind the cutting edge.
That's insane. And eventually that crater grows so large that the cutting edge simply collapses.
Exactly.
What about frittering and thermal cracking?
Frittering is a mechanical failure, microscopic chipping along the incredibly sharp cutting edge. It's usually caused by vibration, chatter, or a lack of rigidity in the machine setup.
And thermal cracking.
Thermal cracking is characterized by tiny fissures running perpendicular to the cutting edge.
Is that caused by the coolant?
Yes, it's caused by thermal shock, which is often exacerbated by inconsistent coolant.
Oh, so.
Well, imagine a milling operation where the cutter is entering and exiting the part continuously. When the insert is buried in the metal, it heats up to 1,000 degrees.
And the millisecond it exits the cut, it is blasted with 50-degree liquid coolant.
Right. It violently quenches and shrinks, then it slams back into the hot metal and expands.
And that rapid expansion and contraction cycle causes the carbide binder to fatigue and crack.
Precisely.
I've actually seen machinists completely turn the coolant off when using certain high-performance ceramic tools for that exact reason.
Oh, yeah.
They run the tool dry, just blasting air to clear the chips because the ceramic can handle the sustained extreme heat, but it will shatter instantly if it experiences thermal shock.
That is a perfect example of adjusting the process to the material properties.
The complexity scales even further when we look at specific operations like tapping a threaded hole.
Tapping is inherently difficult because the tool is buried completely inside the workpiece. You have zero room for chip evacuation.
And tapping hard rubber or advanced plastics seems like a completely different universe than tapping steel. I mean, the handbook rules are wild.
They really are. If you are tapping hard rubber, the material doesn't form continuous chips. It powders.
So if you use standard liquid cutting fluid,
You turn that powder into a sticky, abrasive paste that will instantly bind the tap and snap it. You have to run it completely dry or with a high-pressure air blast.
and in plastics. I've tapped acetyl and nylon before, and it always feels like the material is actively fighting me when I try to back the tap out.
That is because polymers exhibit significant elastic recovery.
Elastic recovery.
Yeah. When the tap is driving the thread profile into the plastic, it is physically stretching the long-chain macromolecules out of the way.
And the moment the cutting edge passes, those molecules snap back.
Exactly. The hole actively shrinks around the tool.
So how do you counteract that?
The machining data specifically dictates using oversized taps for plastics. A standard tap just won't work.
And you also need massive chip clearance, right?
Right. Handbooks often recommend using high-speed steel taps with only 2 flutes rather than 3 or 4. It gives the stringy plastic chips room to evacuate without clogging.
Okay, this brings us to what I think is the most critical realization in the entire machining process.
Let's hear it.
When a tool is struggling, when the machine is groaning, the end mill is chattering, and the finish looks terrible, every human instinct says, back off, slow the spindle down, reduce the feed weight, take it easy.
And acting on that instinct is exactly how you scrap an expensive aerospace component.
It violates everything your brain is telling you. But why is slowing down fatal?
Let's go back to our work-hardening austenitic stainless steel.
Okay.
If you reduce the feed rate, meaning the tool advances very slowly into the material per revolution, the cutting edge isn't taking a deep enough bite.
So instead of shearing the metal, it just aggressively rubs against the surface.
Exactly, generating massive friction.
Massive friction, which instantly work hardens that localized surface layer.
Yeah.
The crystalline lattice just locks up.
Now, on the very next revolution, your cutting tool is trying to penetrate a layer of material that is significantly harder than the raw stock was a second ago.
And the cutting edge gets destroyed almost instantly.
Yep.
So what is the fix? Do you push it harder?
You must increase the feed rate. You force the cutting edge to bite deeply, aggressively punching through and getting completely underneath that shallow, work-hardened layer.
Oh, so you're shearing the softer virgin metal below.
Exactly.
It's the exact same logic with a built-up edge, right? Where the metal literally pressure welds itself to the tip of your tool.
Yes. Built-up edge ruins your surface finish and completely changes the geometry of your tool.
It's like a snowplow pushing wet, heavy snow.
That's a great analogy. If the truck dries too slowly, the snow doesn't slide off the blade. It packs up, sticks, and suddenly your plow has a completely different shape.
Leaving a huge mess behind it.
Right. To fix it, the truck has to speed up to impart enough kinetic energy to throw the snow clear.
Exactly. With a built-up edge on a cutting tool, you often have to significantly increase your cutting speed.
Because it generates enough localized heat in the shear zone to plasticize the material. It allows it to slide smoothly across the tool face instead of welding to it.
You literally have to tune the violence.
Tune the violence. That's good. You should put that on a shop wall somewhere.
I just might. Okay, we've successfully navigated the physics of machining. We've sheared the metal, managed the heat, and evacuated the chips.
But did we cut it to the right size?
Yes. The final hurdle in the physical world is tolerances and fits.
Making a part is one thing, but making it interact with another part is the core of mechanical engineering.
And we govern these interactions using standardized limit and fit systems, like the ANSI standards for cylindrical parts.
Essentially, the relationship between a shaft and a hole.
Precisely. The standards define three primary operational categories.
Right. Yes. First is the clearance fit. It's mathematically designed so that even if the shaft is machined to its absolute maximum allowable size and the hole is machined to its absolute minimum size, there will still be a physical gap between them.
So they will always slide freely.
Exactly.
Then you have the interference fit, which is the exact opposite.
Right. A press fit or a shrink fit. It guarantees that the shaft is always physically larger than the hole.
You have to use tons of hydraulic force to press them together.
Or use thermal expansion, freezing the shaft in liquid nitrogen while heating the bore in an oven. Once they normalize, the physical interference locks them together permanently.
And the middle ground is the transition fit.
A transition fit has overlapping tolerance bands. Depending on where the specific parts fall in their manufacturing curves, you might end up with a very slight clearance or a very slight interference.
Which is generally used for precise locating, like lightly tapping a dowel pin into place.
Right, where you need exact alignment but not permanent heavy force.
So how do we communicate the precision required for these fits on the blueprint? We don't just write, make it tight.
No, we use standard tolerance grades, specifically the IT grades or international tolerance grades.
And the scale is inverse, right? The lower the IT number, the tighter and more precise the tolerance band.
Yes, and this directly dictates the manufacturing process.
Because the manufacturing process limits the achievable precision.
Absolutely. If a print calls out an IT4 or IT5 grade, you are demanding extreme precision. A standard lathe or milling machine cannot hold that reliably.
The shop will have to use specialized abrasive processes like cylindrical grinding, honing, or lapping to slowly sneak up on that dimension.
But if the print specifies an IT10 or IT11, a standard drilling or turning operation is perfectly acceptable.
And this ties intimately into surface texture. The precision of the dimension is often useless if the surface is too rough.
We measure this primarily using raw, the average surface roughness. You simply cannot hold an IT 5-dimensional tolerance if your surface looks like a mountain range under a microscope.
Because the peaks of that mountain range will quickly wear down, and suddenly your tight dimension is lost.
Exactly. The manufacturing process establishes the floor for the raw value. Sand casting produces a heavily textured, rough surface.
But to achieve a low raw value, a near mirror finish, you must mandate processes like diamond turning or lapping.
I think one of the most eye-opening parts of this process is realizing that the tolerance on the blueprint isn't the actual target the machinist gets to use.
Oh, this is the best part. We have to dive into the statistical realities of quality control.
This is where the math of mass production comes in. When a CNC machine turns out a batch of 1,000 shafts, they aren't all identical.
Right. Their actual measured diameters will naturally form a normal distribution curve, a statistical bell curve.
And the width of that bell curve represents the machine's inherent capability.
And obviously, the entirety of that bell curve must fit inside the maximum and minimum limits drawn on the blueprint.
But here is the catch. The inspector doesn't have a magical, perfectly accurate measuring tool. They use physical gauges, like a ring gauge.
And because that gauge is a manufactured physical object, it has its own manufacturing tolerance, right?
Yes, called the gauge maker's tolerance.
Wait, so the tool checking the part could be slightly wrong.
Yes. The rule of thumb is that the gauge maker's tolerance uses up about 10% of the total workpiece tolerance.
Wow.
Furthermore, as the inspector slides that hardened steel gauge over hundreds of metal parts, the gauge physically wears down.
So engineering standards dictate that you must also leave a wear allowance for the gauge inside the tolerance band.
Right, so the actual window the machinist is trying to hit is significantly smaller than what the engineer wrote on the drawing.
Because the gauge maker's tolerance and the wear allowance consume the outer edges of the blueprint tolerance.
Exactly. If a part falls into that gray area, the gauge might reject a part that is actually technically within the blueprint limits, simply because the gauge itself is at the edge of its own tolerance.
And this reality leads to one of the most expensive blunders in our industry: over-tolerancing.
It is devastatingly costly.
Engineers sit at their CAD stations, completely isolated from the reality of the gauge maker's tolerance in the bell curve, and just assume that tighter tolerances automatically equate to a higher quality product.
There is a brutal exponential relationship between tightening a tolerance grade and the manufacturing costs required to achieve it.
Let's walk through an example. Say I'm designing a basic pivot shaft for a slow-moving, non-critical lever arm.
Okay.
It just needs to sit there and let a bronze bushing rotate around it once a day. If I just blanket apply an IT5 tolerance to that shaft, what happens on the factory floor?
Well, the machine shop receives your drawing. They
Yep.
look at that IT5 cal out. They know their standard CNC lathes, vibrating slightly on the shop floor with standard carbide tooling,
Yeah.
cannot reliably hold that tight of a statistical bell curve.
So instead of just turning the shaft in one quick operation on the lathe, they have to add a second operation.
They have to leave the part slightly oversized, pull it out of the lathe, and move it to a cylindrical grinder.
Which requires an entirely different, highly expensive machine.
It requires a new setup time. It requires a specialized operator. It requires specialized inspection gauges, which are also exponentially more expensive to manufacture to that tight tolerance.
And because the margin for error is microscopically small, the rejection rate of parts goes way up.
And the worst part is, the final assembly didn't need any of that.
The lever arm would have pivoted perfectly fine on an IT10 shaft that cost 1/10 the price.
Exactly.
I frame this for young engineers all the time, using a kitchen analogy. Over-tolerancing is like demanding a surgeon come to your house and use a laser-guided, diamond-edged microscopic scalpel to slice your morning bagel.
That's hilarious.
Will it result in two halves of a bagel? Yes. But you just paid $10,000 for a result that a $2 butter knife could have achieved flawlessly.
The golden rule of tolerancing is absolute. Only specify the widest tolerance and the roughest surface finish that still allows the part to function perfectly in its application. Anything tighter is simply burning money.
The bagel and the scalpel. Never forget it. All right, to wrap up this masterclass, we're going to open the doors for Section 6, Office Hours.
I love this part.
We've scoured engineering forums, Reddit threads, and online communities to pull the actual real-world debates engineers are having about these specific topics, and we're going to apply the physics we just learned to solve them.
Let's hear what the community is struggling with.
Okay, first up, I was reading a heated thread yesterday on a controls engineering forum. A junior engineer was tasked with designing a stabilizing controller for a new quadcopter drone.
Oh, that's a classic multivariable problem.
Right, and they were arguing with a senior engineer about how to model the dynamics. The junior guy wanted to use a classical input-output model, but the senior engineer was demanding a state variable model. What is the fundamental difference, and who is right?
Well, the senior engineer is absolutely right in this context. It goes back to the complexity of the system.
Okay, unpack that.
An I/O model, or input-output model, treats the drone like a black box. You map a specific input like moving the joystick forward to a specific output, like the drone pitching down.
This classical approach using transfer functions is fantastic for simple single input, single output systems.
Like a basic thermostat in a house. The input is the temperature setting, the output is turning the heater on.
Exactly. But a quadcopter drone is a highly complex, multivariable system.
Right. A wind gust hits one corner. The drone pitches, rolls, and yaws simultaneously. All four motors have to react independently but cooperatively.
If you try to map every possible input to every possible output using a black box I/O model, the math just becomes unmanageable.
So what does the state variable method do differently?
Wait, I was going to ask you that.
Right. Well, state variable modeling cracks open the black box. Instead of just looking at the outside, it defines the system by its internal states, the internal energies, momentums, positions, and velocities of the components at any given moment.
Oh, so by utilizing matrix algebra, state variable methods track how the internal dynamics govern the behavior.
Yes. If you need to control a multivariable system with complex internal interactions, you must use a state variable approach.
That tracks perfectly with what we discussed about lumped elements. Okay, moving on to the factory floor. Here is a post from a machinist forum. I'm turning a large Inconel shaft. I'm using a premium titanium nitride coated carbide insert, but the top face keeps cratering out after only 3 passes. The cutting edge collapses. What do I change?
Inconel, a notoriously tough, high-temperature superalloy.
Yeah. Cratering, as we established, is primarily a chemical wear mechanism driven by extreme heat at the tool chip interface.
Right. The Inconel is essentially dissolving the tungsten carbide binder. The handbook provides a clear hierarchy of troubleshooting.
Where do you start?
First, since he is already using a coating, he might need to switch to an entirely harder substrate, perhaps a ceramic or CBN tool, which chemically resists cratering better than carbide.
But assuming he is locked into using carbide tooling for cost or rigidity reasons, how does he alter the physics of the cut?
He has to aggressively manage the heat. The primary driver of cutting temperature is surface speed.
So the first mechanical fix is to reduce the RPM of the lathe, slow the cutting speed down.
Exactly. But if the cratering persists, he needs to look at the chip breaker geometry on the insert itself.
The physical groove molded into the top of the cutting tool.
Yes. If he switches to an insert with a wider, more open chip breaker groove, it alters the curl of the hot chip.
Oh, I see. Instead of the chip curling tightly and dragging heavily across the face of the tool, generating massive friction and heat.
A wider groove allows the chip to flow more freely, carrying the heat away from the cutting zone faster.
It always comes back to heat transfer. Okay, here is a question about fluids. On a piping design subreddit, a student is pulling their hair out.
Poor kid. What's the problem?
They say, I'm sizing a pump for a cooling loop. I know I have to iterate the Colebrook equation, but doing it manually is taking hours, and my initial guesses keep diverging. Is there a visual way to plot this iteration?
Yes, there's a brilliant classical textbook trick for solving this without getting trapped in endless algebraic loops.
A visual trick.
Yeah. Instead of blindly guessing friction factors, you embrace the entire range of possibilities visually. You choose 3 or 4 widely spaced, arbitrary fluid flow rates.
Say 100 gallons per minute, 500, and 1,000.
Exactly. For each of those assumed flow rates, you can easily calculate the required velocity, the Reynolds number, the friction factor, and finally, the total head loss through your pipe system.
Okay, then what?
Then you plot those points on a graph. Flow rate on the x-axis, head loss on the y-axis. Draw a smooth curve through them. This is your system curve.
So that curve represents the physical resistance of the pipe network across a whole range of speeds.
Now, look at the pump you are trying to use. The pump manufacturer provides a pump performance curve, which plots the head pressure the pump can generate at various flow rates.
Oh. You overlay the pump curve onto the exact same graph as your system curve,
And where the 2 lines intersect.
where the available pressure from the pump perfectly matches the physical resistance of the pipe. That intersection point is your operating reality.
You just look down at the x-axis and read your exact flow rate. It visually solves the complex interdependent iteration instantly.
I absolutely love when a graphical solution cuts through the algebraic noise.
It's elegant.
Final question. This one goes back to our thermodynamics discussion, an engineering debate about energy storage. When analyzing a pressurized hydrogen tank for fuel cell use, my textbook distinguishes between its physical exergy and its chemical exergy. What is the actual difference?
That is a fundamental thermodynamic distinction. Remember, exergy is the maximum theoretical useful work we can extract from a system as it equalizes with the ambient environment.
The dead state.
Right. Physical exergy relies entirely on the mechanical and thermal differences.
Okay, so imagine the tank is filled with highly pressurized hydrogen gas at 3,000 psi, but it is sitting at room temperature.
The physical exergy is the mechanical work you could extract if you hooked that tank to a pneumatic turbine, letting the high-pressure gas expand and spin the turbine blades until the pressure inside the tank dropped to match the atmospheric pressure of the room.
But once the pressures are equal, the turbine stops spinning, the physical exergy is completely depleted.
Exactly. But the tank is still full of hydrogen gas. That hydrogen hasn't equalized chemically with the surrounding air.
It still possesses massive chemical exergy.
Yes. This is the work you can extract by utilizing the difference in chemical composition. If you run that ambient pressure hydrogen through a fuel cell, reacting it with the oxygen in the air, the chemical reaction releases a tremendous amount of electrical work.
So physical exergy is derived from pressure and temperature gradients, while chemical exergy is derived from the molecular potential to react with the environment.
You extract the physical exergy by expanding it, and the chemical exergy by burning it or reacting it.
If you look at the through line of this entire deep dive, whether we are talking about balancing the taxes of entropy in a heat exchanger, the mathematical difference equations in a drone's dynamic model, or aggressively managing the heat dissipating from a carbide cutting tool in a block of Inconel,
Yeah.
engineering is universally about managing energy and material within the most efficient, cost-effective physical constraints possible.
It truly is. And that leads to a final thought I want to leave with the listener today.
Lay it on us.
Think about the entire life cycle, the brutal evolution of a single engineered component. In its infancy, it begins as a perfectly frictionless, massless mathematical concept in the mind of the designer.
Pristine and perfect.
Then it is violently forced to face the physical reality of entropy, fluid friction, and finite time during the thermal analysis.
It pays the universal tax.
Right. Next, it gets physically beaten and sheared out of a block of work-hardening steel on a milling machine, fighting chatter in extreme heat every millimeter of the way.
Only to end up in quality control.
Exactly. And finally, after surviving all of that physics, it might just get tossed in the scrap bin by an inspector because someone drew the tolerance band on the blueprint 1/1000th of an inch too tight.
The scalpel and the bagel.
Engineering isn't just about executing math. It is about expertly navigating the endless, painful compromises between the perfect mathematical ideal and the chaotic, messy reality of the physical world.
If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.